Good day. I am Mikhail Goldonis, and for my course project in data communications and networking, I was asked to choose from a bank of topics the selected group of topics that I wanted to report about, and I chose the second group, which happens to be the layers of the Aussie model that focus on the lower part of the Aussie model or the bottommost layers of the Aussie model. And those layers are the physical and data link layers, the network and transport layers in um, the Aussie model. So, without further ado, let us get into the discussion. So for the lowest layer of the Open Systems Interconnection Model or OSI model, we have the physical layer, which is responsible for transmitting raw data bits over a physical medium. It deals with the actual hardware being a physical layer, and also the connections involved in data transmission, such as the cables, the switches, and the radio frequencies. Its services include bit level transmission, bit synchronization, physical connection, setup and termination, and also line coding for data transmission, also flow control and start-stop signaling, multiplexing, collision detection and warning, and forward error correction. So the protocols it uses in order to implement its services include the Ethernet and DSL for wired connections, Bluetooth, the USB or the Universal Serial Bus, an integrated services digital network for systems or systems that do not involve DSL, also an infrared data association, and a controller area network. Now let us move to the second layer of the Aussie model, which is the data link layer. So, because it is the second layer, it sits above the physical layer and ensures reliable data transfer between two directly connected nodes. Through encoding and decoding, it breaks down data into frames and provides error detection and correction. It has multiple sublayers, the first being the media access control or MAC, not Macintosh, as in the one in Apple, but media access control, which defines how devices on a network gain access to transmit data. And this MAC has two forms. It could be distributed, which means it will operate in a decentralized manner, wherein devices negotiate across access across media and independently decide when to transmit, or it could be centralized, which means that devices rely on a central controller that manages access to the network medium, often at specific or set times. So let's move on to how that works. So it involves frame synchronization. So as a while ago, I said that it could be time based, and yes, that is one of the methods of frame synchronization, or one of the methods of frame synchronization used by the Mac in order to in order to configure how devices on a network gain access to transmit data. So, aside from being time based, there is also such a thing as character counting. This is another method of frame synchronization, which counts characters or bytes in a frame for synchronization. And then there's also flag based, which uses flag characters to mark frame boundaries. And finally, there is also the bit oriented approach, which means synchronization occurs by patterns in bit streams using HDLC. So HDLC basically means that there is a protocol called HDLC, which is used for transmitting data between devices in telecommunication and networking. So that is what it is: high level data link control. So, moving on, there is another sublayer that can be found in the data link layer, which is called the logical link control or LLC. It operates above the MAC sublayer and is responsible for identifying network protocols and handling data traffic flow through error checking, ensuring error-free communication across the network. So for a demonstration of how the physical layer works, I decided to create a simple model in Cisco Packet Tracer, which is based on one of my laboratory activities that I previously also recorded on YouTube. In particular, the third laboratory activity, and this is the basic this is the basic model on how a physical layer works. So basically, these um these cables or straight through cables are connected to our PCs or one PC each, and they link the PCs to a hub or a switch in our simple or small network. While the bridge over here, which is a new configuration or a new device that I added from the original configuration I had with my laboratory activity, it is connected to the switch and the hub using a coaxial or not a coaxial, using a crossover copper cable um, connecting them. So basically, the physical aspect here is for the zoom. The physical aspect over here is the use of the cables in connecting them to the respective ports or the fast Ethernet ports, as over here in the configurations, connected to the fast Ethernet ports of our various PCs. And yes, so that is how our physical layer works in this setup. So let us simulate this for better understanding. So as you can see, the bridge distributes the data packet to the hub and the switch does not drop it. It checks the packet, but it sends it to the PCs where the packets are dropped. So that is just as simple as it is. And since the data packet or the data link layer is closely associated to the physical layer, we can say that the data link layer is covered also in our simple network simulation, as the data link layer sits above the physical layer, and the reliable data transfer is demonstrated by the um, the switch transmitting the data packets to the two PCs over there, and two PCs connected to it, and same with the hub. Although the hub has less security, as it only transmits whatever is incoming, and it doesn't do any foolproofing or checking. But as it is still a demonstration of the physical and data link layers. Now let us move on to the network layer, which is the third layer in our OSI model. It handles the routing of data from the source to the destination across multiple networks and decides the best path for the data packets to be forwarded, considering factors like network congestion and link quality. So this is the part or the layer wherein we will be able to see the use of routing. Hence, we will encounter a device called a router, which is an intermediary device, that is its classification, as it forwards data packets between networks by ensuring that data reaches the correct destination through the reading of a destination host address that is found in the data packet's header. Its types include a home or a small office router and an enterprise router, which are obviously differentiated by the scope in which they are used. The home being a small scope and the enterprise being a large scope. So, yes, routing involves choosing the best possible path for data traffic in a network or across multiple devices, while packet forwarding is the actual transmission of logically addressed data packets from one network interface to another. Now, obviously, aside from the routers, there are other devices that are used to facilitate the routing process. So this includes switching through switches and bridging through bridges. But the bridge basically connects intermediary devices and or end devices, and as such, it is limited as compared to the routers and the switches. So we've already talked about routers, but let's talk about switches this time. So what is the process of switching or using switches? It is the process of directing traffic between multiple network paths, and so it comes in two types. So there are two main types of switching. The first being packet switching, wherein data is broken into small packets or variable bit rate data streams, which are independently routed through the network through statistical multiplexing. So this is the second time that we've seen the word multiplexing. What exactly does it mean? Well, multiplexing is basically the process of combining two or more information channels through into a single transmission medium. So basically, it is being combined into a switch, which the switch acts as a single medium when the information comes in from different end devices or network devices that also transmit information that comes from end devices. And so, yes, so that's how it works. That's how multiplexing works. But if statistical multiplexing is not used, dynamic bandwidth allocation is also an option. So in a scenario where an internet provider or your telecommunications provider bills you for your internet and charges it according to the packet switching method or the packet switching configuration, the charges that are being placed onto you are usually for the information transmitted between the receiver and sender. So this is more applicable for the traditional SMS Yes, the traditional SMS layout or standard messaging system, wherein, of course, our Globe, Talk and Text, or Smart, whatever network provider you are using, will charge you if you send a text with more characters more or more media included, such as pictures and etc. Obviously, this is before the messenger days and social media days, and so um, that is um, that is how telecommunications used to work back then. And now we move on to circuit switching, which is a dedicated communication path between sender and receiver, um, being assigned for each session as demonstrated in, once again, I will use the scenario of traditional telephone networks, this time in a payphone setting, not a SMS setting, since the payphone setting is the most appropriate situation to use for circuit switching, as when you use a payphone, you are charged for the amount of time you spend on a call and not for the amount of content that is one being transferred from one end of the telecommunication line to another, or even in a standard call on a cell phone. So yes, the situation being talked about here, once I repeat, is a payphone or a regular or an old cellular phone conversation wherein the billing charges are for the time spent in the particular connection, and as a result, this model or this type of switching isn't flexible, and therefore it is less efficient and more costly, which is why I am very very glad it is being phased out in favor of, well, fiber optic communication through the internet. So over here, I have another network in Cisco Packet Tracer, another mini network, to demonstrate the network layer of the OSI model. Although, I could still go back to the physical layer, as this particular layer has a physical component installed in order for the transmission of data or the routing of data to properly work, since we have two routers, and it is this port over here which enables the serial this card over here, sorry, this card, it is a card that enables the serial port in the router that we have, this one being the serial 0 01 port, and that is also the same for this one. This also has a card over here that enables the serial 01 port of our. As you can see, the on is checked. The on option is checked. The serial 01 port of our two routers. But since we have two routers over here, let us just use this setup to demonstrate the network layer of our OSI model. So let us simulate the transmission of data. So as we can see, the switch transfers data packets over to the PCs which are dropped, and it also transfers it to the router which is also dropped as well. And for the most part, the data is always starts from this switch and is always being transmitted outwards to the router and to the PCs, and only every once in how many minutes will the data be transmitted from this router or router 4 to our router 3. As seen once again, it is the switch that transmits data packets or forwards them to the other components. But basically, that is how our routing works. So yes, I'll try to speed it up to see if there are any changes. So far, there are no changes as of the moment. And yes, that is our first change. As I sped it up, the switch transferred it to PC, transferred the data packet to PC1, which PC1 obviously dropped, and it repeated the process once again. So yes. For our final layer in this discussion and the fourth overall layer in the Aussie model, we have the transport layer. So this layer ensures the transportation of data, which means that the data is completely transferred by providing end-to-end communication services between applications across different devices. So therefore it establishes, maintains, and terminates connections. So that being said, of course, its services must include reliable data transfer, flow control, avoiding congestion, once again, multiplexing, same order delivery, and connection based communication. It works by breaking large data into smaller segments for transmission or segmentation, adding control information to each segment for error checking and flow. Now, upon receiving the data, the transport layer reassembles the segments, as I said a while ago, through the transmission protocol being activated. And so, this is a very important protocol in the operation of the transport layer as it checks for errors that may be resolved by another protocol which is called the automatic repeat request protocol before it passes the data to the application letter. But if the data packet that arrived has no errors, then it may be able, the TCP may bypass the ARQ or the automatic repeat request protocol and send the data immediately to the application layer. So the TCP is one of the most important protocols in the transport layer, as without it, well, the checking or the evaluation of the data being received by the device will not it will not be foolproof. It will not be good at all. So aside from the TCP and the ARQ, there are many other protocols that derive that are derived from these, but there's only one other important protocol, which is the UDP or the user datagram protocol, since it provides fast collectionless data transmission without error correction. So this one doesn't need error correction from the TCP or the ARQ, and therefore it is suitable for time sensitive applications like our very own YouTube and Vimeo and other video streaming applications. And for our transport layer simulation over here in Cisco Packet Tracer, I once again copied another network model from one of my laboratory activities. I just changed the website name for obviously differentiation purposes, but this is basically the same model that I had in my fifth laboratory activity. So before we enter if our website works, we are going to simulate the chain of events happening. So as you can see, the switch forwards a few packets to the other switch and the other PCs, which then forwards the packets to the servers, which the servers drop. But in a usual what do you call it? In a real-time format, one of the PCs sends a request to the DHCP, and then the DHCP responds with this with the appropriate IP address to the two dynamic PCs over here, since they are dependent on having an IP address from our DHCP server. And then when we are going to search for a website, um, typing in the URL will cause one of the dynamic PCs to send a link or a data packet to the DNS server over here, which will then respond with the IP address or the gateway to the website itself. And once it does that, it will send a data packet back here to this over to the switches to the PC, and then from the PC it will go send it to the web server, which will then find our corresponding domain name or website. So let us try over here on our PC1, since this is one of our dynamic PCs, and I basically copied the format that I did. I just changed the contents that I had from my laboratory 5 activity, and definitely I changed the name of the domain and the URL. So this one is called www.ivanb.com, and this is not not too important info, but this is basically a this web page is basically a tribute I made to one of my favorite rappers, whose name is Ivan B, or Ivan Panigua in real life. So the content over here, I just changed it. I just changed it to for to reflect on the information about a song that he wrote, which is "Walk with Me," which is an EP that he released in 2015, and it is basically a mixtape of another popular song called "Sweater Weather" by the Neighborhood. So anyway, this info was edited over here in our server. So as we can see, as I did in the my fifth laboratory activity, I configured these services over here in the settings. I was able to edit this hello world part and put whatever content I needed. This is the lyrics of a song that I got from Walk With Me, and I also was able to configure the index or the introduction, which contains the text over here, which originally would read everything about Cisco packet tracers. So yes, that is part of the whenever the transfer layer of the OC model is in operation, once it sends the data packets to the DNS server and then to the web server, which will activate our domain, which is or access our domain, which is ivanb.com. It will respond with that content, that perspective content that you can see on the web page over here, and these are the lyrics to a song, to the Walk With Me song that he wrote, and that basically does it for our transport layers. So the data packet is transported to from the DHCP server to the PCs to the DHCP server, then back to the PCs to the DNS, then back again to the PCs to the web server for this to take place. So now that we are done with the demonstration of our four bottommost layers in the OC model and the discussion of them in the PowerPoint or Canva presentation that I have created, let us now move on to part 2 of my course project. And here is part 2 of my course project in Data Communications and Networking 1, where I was tasked to find the missing values in the table given that contains the network address binary of the IP or network address, the prefix length, the subnet mask, the gateway address, and the corresponding broadcast addresses. So yes, the the areas that you were originally missing and have been answered by me, of course, solved and answered by me, of course, are now filled with, over here and are represented with red ink. And yes, so we will now discuss on how they we will now discuss or tackle how they were calculated. So yes, I while I did not I do not have a picture of the way the calculations, I was able to majority of them I was able to solve off the top of my head, and the others, well, I just looked into them and I knew what the answer was since I have basic awareness of the principle. So first item is this one. The prefix length of our network address 172.201.95.32, which yields the corresponding binary address. So the prefix length is denoted by our sub our our subnet mask over here. So two 255, 255, 255. That corresponds to all ones on an eight on our 8-digit binary code. So that means basically over here I have a notepad recording of this. So here, our subnet mask is 255, 255, 255, 224, and you have to convert this into binary in order to find our prefix line. So obviously, 255 means that all the values in our 8-digit binary code are filled, and that means all of them are true or one. And so when all of them are 1 and 3 of them are 255, that means 8 plus 8 plus 8 is equal to 24. So that brings us to 24 of our 24 of our prefix length, while the 224 at the final part of our subnet mask means that not all of them are ones. So basically, the leftmost part of the binary, I'm zooming in, the leftmost part of our binary code, our subnet mask, is the true values. So what does that mean? From right to left, a binary digit or a binary code is operates on the powers of two. So basically, this one is let me zoom it a little more. 1, 2, if you can see my cursor, 4, 8, 16, 32, 64, 128, and 128 plus 64 plus 32 is equal to 224. So 224 yields 3 ones, and adding the 3 ones to our 24 ones, we have 27 ones. And since the prefix length is the number of ones, that yields to 27. So our prefix length is /27, and that's our answer for number 1. Now for number 2, we have the broadcast address, and this is the broadcast address that I came up with. So to find the broadcast address, we first have to refer once again to our subnet mask, which is 255, 255, 255, 224. So what does that mean? That means that the block size is 32. The block size being given by the difference between 256 and 224. So block size is calculated by that 256 minus 224, which is equal to 32. So our next block or the next available IP address, that it starts at 172.201.95.64. So the broadcast address is the one that comes before this block address, meaning that the broadcast address for 172.201.95.32, as given over here, the network address, we just need to add 21 to that. So basically, that is 1, or not 21. We basically need to subtract 1 from this one over here. So it means that our broadcast address is 172.201.95.63. Now on to our number 3. The number 3 item that I needed to solve, which is the subnet mask over here. So the subnet mask over here at number 3 um, is easily solvable through the prefix length. So if the prefix length is given, then we can solve for the subnet mask. So with the prefix length being 25, as usual in the subnet, we often assume that once we reach 24 and above, that our ones are, what do you call that? Our ones are all complete in the 8-digit binary code. So just like in number 1, the ones are all complete. So that means that 1, 2, and 3, or 1, 2, and 3 of our part 1, 2, and 3, or segment 1, 2, and 3 of our binary code are all ones, and therefore all of them are 255. So automatically we have 255, 255, 255, 128. Now, the other one, which means 24 plus 1 is equal to 25, and that's our prefix length, right? Right? The other one is from the leftmost number of our binary code. So our binary code, then we type it over here. Segment 4 of our binary code is 1000000, and that is it. So only 128, the 128 segment of our binary code is true, and therefore that means our subnet mask for this specific IP or network address is 255.255.255.128. And for our gateway address over here, the gateway address is simply the first usable address in the subnet, which is the next IP after the network address. So basically, for solving the gateway address, all we have to do is add 1 to the outermost or the rightmost digit of the final segment or the final number of our IP or network address. So if it is 128, all we need to do is add 1 and we get 129 or 10.10.78.129, and that is just what I answered for item number 4. Now for item number 5, this one is easy. All we need to do is to basically convert the following decimal numbers in our network address into binary numbers. So what we do is this one. um, 192, 84, 32, 35, and then we split them into segments. So obviously the last part is 0. So all of the um, digits in the binary code are false. Over here, 235, the, the digits that are true in our binary code are 132, 64, 32, 128, 64, 32, 8, 2, and 1. So let us open up our calculator and see how that goes. Just to check if we are correct. 128 plus 64. Hold on. 64 plus 32. 16 is false. So and 8 is true and 4 is false. Plus 2 plus 1, and we have 235. So that is correct. That's the third segment. For the second segment, um, our only true values are 64 and then 16 and then 4. So 64 plus 16 plus 4 is obviously 84. And then for 192, 128 plus 64 is also automatically equal to 192. And that is the binary representation of, when we combine this, that is the binary representation of our network address over here. So that is correct. And then the broadcast address, once again, the broadcast address, once our broadcast address is 0, that means that the block size is 256, since 256 is the maximum block size. And therefore, the broadcast address, all we have to do is subtract 1 from 256, and that is our corresponding answer. So 192.84.235.255, or 256 plus 1. Always remember that the subtraction or minus 1 occurs at the last segment of our IP address or network address. So that is our 1, 2, 3, 4, 5, 6, our number 6 item. And then for our 7th item, we have the prefix length once again, and all we have to do is find it based on the conversion of the subnet mask. So once again, we are going to convert our subnet mask, which is 255, 255, 255, 192, and then obviously this automatically yields, since it is 255, and that means all 8 digits in our binary code are true. This automatically yields a prefix length of 24 plus our 192, which means that our leftmost digits are are true. So 1 plus 1 is equal to 2, and add 2 to our prefix length of 24. That means our prefix length is 26 or slash 26. And then that leads us again to our broadcast address. So for our eighth item in this part two of my course project, all we need to do to find the broadcast address once again is to subtract 192 by 256. So 192 or 256, sorry, and 256 minus 192 means the block size is 64. So let us check that when using the calculator. Calculator. 256 minus 192, and there we go, 64. So that means that the next block starts at 128, since 256 minus 64 is sorry, that means that the next block starts at 172.99.184.128. So that means that we add 64 to our IP address or our network address, and we to find the broadcast address, we just subtract 1 from the last segment of our IP address. So 128 minus 1 is equal to 127. And just to recap, that is the answer that we got for number 8 over here. That is also the same process that we did for number um, number 6, which is basically adding 256 or the corresponding block size to the last segment and then subtracting it by 1. And that is also what we did for our number 2 item, which means we added 32 to our last segment, or the fourth part of our broadcast address or IP address. 32 plus 32, 64, and then minus 1, we got 63. So that is it for number 8 over here. And then number 9, the binary address, all we have to do is just calculate it by converting it into decimal numbers. So here is number 9, and then all we have to do is convert 205, 36, 72, and 56 into respective decimal numbers. So that would involve calculation using this calculator. 128, we're going to calculate only the one value, 6 plus 64 plus 16 plus 8, or sorry, minus 16, sorry, 16 is um, not true, plus 8 plus 4 plus 1, and that is 205. So our 205 is correct. And then 36, we basically added 32 plus 4. And then for our 72, that is 64 plus 8. And then for our 56, that is 16 plus 32 plus 8. And that yields 56. And um, we combine all of these in order, and that is our binary representation or our binary answer for number 9. And then for number 10, once again, we are being tasked to find our broadcast address. So all we have to do is subtract 256 from 248, then we have 8, and then we add 8 to 56, we get 205.36.72.64, and then we subtract 1 once again, and our broadcast address is 205.36.72.63. And that wraps it up for my course project in data communications and networking 1. Thank you for watching and have a nice day once again.